All right, we're going to start Unit 3. Let me turn the slide off here. And this is a really important chapter. I mean, all of the chapters are, but this one especially for anyone that's going on to take more chemistry classes, because acid-base chemistry, this is really the basis behind all reactions. So I even tell my organic students that organic chemistry is simply acid-base reactions. Okay, of course, it's a lot more complex than that because you have to recognize different acids and bases, and you really get into more detail. But it all starts here. So our acid-base theory. And the very end of this chapter we won't get to today, we talk about the Lewis theory. So that's the same guy as did the Lewis structures that you've learned to draw. Okay, and it's really the best theory as far as for leading you into organic chemistry. Okay, so we're going to touch on that, and we're going to see that. I have a list to send around. This will be a list that you'll get with your exam. Okay, so you don't have to memorize it, but you'll start to kind of memorize it anyways because you're going to use it a lot. Okay, it's a strong acid, strong base list. Whoops. Okay, and then we can add to this list if we run into more strong acids and bases that we want to use. But basically, this is going to be not as important necessarily today, but it will be through the chapter. But if it's on this list, that means it's a strong acid or a strong base. So if you notice here, so some of these you've probably heard of before: hydrochloric acid, okay, hydrobromic acid. Notice that one that's not on here is HF. Okay, a lot of people accidentally just assume that it is a strong acid, but it's not quite strong enough, and we'll talk about why today. Granted, it is very toxic, very dangerous to work with, so, but that's because of the fluorine and the fluorine gas that it can generate. Okay, but it's not considered a strong acid. Okay, strong base, a lot of these are hydroxides. Okay, so if you go down, okay, and then there's a couple little notes at the bottom there. So if you look at the star where it says H3O+, we'll talk about what that is today, but it's hydronium. And then H+, those are the same thing. Okay, I'll show you what that means here in a little bit. But this is an acid. That's what an acid produces, is H+ and H3O+. So if you see that anywhere, you consider it to be strong. Okay, so how this is going to be handy is because we can have this list of strong acids and bases, but there are thousands of acids and bases that we can, choose from or use in the lab or whatever. So if it's not on this list, then what do you think you assume it to be? Weak or strong? Weak, exactly. So it helps you by process of elimination. If you know these are strong and it's not on this list, then it's got to be weak. Okay, and that's going to become important to us when we're trying to do some acid-base chemistry and reactions. Okay, so here's just a few properties. So in your book's got some more, properties of acids and bases. But first, looking at the properties of aqueous. Aqueous just means in water, okay, acidic solutions. These are usually sour in taste. Okay, they will change indicators. So you've seen this. You've done this in the lab quite a few times. So they change the blue litmus paper to red. Okay. They also turn indicators. So bromothymol blue, that's an indicator. Okay, so they turn indicators different colors. Okay, when acids react with metals, they produce hydrogen. Okay, hydrogen gas, which can be dangerous. They form salts in water, and they react with metal oxides. So we'll see all this later. These are just highlight points. Okay, they'll react with salts of weaker acids, okay, to form the weak acid. We'll talk about that some more too. And they will conduct electricity. Okay, so in Chem 111, if you had it at Calhoun, does anybody remember the chemical bonding or chemical properties lab where you had the little electrodes? And you went around and you went in the different solutions and you tested it and you pushed the side. I would actually like to do that again in Chem 112, or actually move it. We've talked about it because this is when you start to really understand what you were doing in that lab. So, some of it did pertain to Chem 111, but a lot of it pertained to acids and bases and knowing about them. So there was questions at the end that I either didn't make you do or we talked through them, and they were beyond the scope of, it kind of went over everybody's head. Well, after learning about acids and bases, those questions you would be able to answer now. So it's just a little premature. Okay, so they will conduct electricity. So the more acidic the solution, the more ions are produced. Okay, and we'll look at equations today to show that. Okay, and things, household liquids, soft drinks, vinegar, fruit juices, these are all examples. So there's, list could go on and on of acidic solutions. Base is kind of the opposite. Okay, so they have a bitter taste. Okay, they have a slippery feel. Okay, and they will turn red litmus paper to blue. You've all seen this also in the lab. Okay, they react with acids to form salts and water. So this is a big one. This is called a neutralization reaction that we'll go over. And they also conduct electricity. So they produce ions, okay, and they will conduct electricity. Okay, so a lot of our cleaning materials that we have in our homes are basic, okay, including ammonia. Okay, so it's actually a weak base. Okay, most of your cleaning materials are diluted, so that they're not extremely strong acids or bases, just from a safety standpoint. Okay, so that was just some general ideas about acids and bases before we get started. Okay, but we're going to look today, we're only going to get to two theories. Okay, one is the Arrhenius theory. It's the oldest theory, okay, and it's still true, but it doesn't encompass all acids and bases. Okay, so we've added to this as time has gone on. Okay, the Arrhenius theory was back in 1884, so obviously a long time ago. Okay, and he said that acids contain H+ in aqueous solution. Okay, so I'm going to keep up with this. Okay, so this was his definition of an acid. Okay, is that an acid contains H+ in aqueous solution. Okay, so what's aqueous mean? In water, exactly. So he basically said that your acids and bases could only be put in water, right? They will only react in water. Okay, so here's two examples, and we'll talk about how we can predict products and everything later. Okay, but here's HCl, all right? Is it a strong or weak acid? Strong, because it is on your list, exactly. So in water, it will react to form H3O+ and chloride, and we'll work on being able to figure that out. Okay, and then here we also have an acid with this is formic acid. Okay, so it's going to be a weak acid. Right, it's not on your list there. It reacts with water and forms the H2O+, and this is called a conjugate base, and we'll talk about that too. All right, so if we look at these two, what's this? What's these arrows mean? Okay, what was your last chapter titled? When we had double arrows. I just took the test and then gone. Okay, what does it mean when the rate of the forward equals the rate of the reverse? The reactions are in equilibrium, exactly. Okay, but why isn't this one, do you think? It's not in equilibrium. What's the difference in these two? Okay, you already told me this, right? This was strong. Okay, a strong acid means that it completely ionizes, completely reacts. So every bit of that HCl, when it was put into water, becomes H3O+, that's hydronium, and chloride. Okay, but here, is this weak or strong? This is formic acid. So do you see it on your list? It's weak. Okay, it's a weak acid. Okay, so some of it will react with water to form the hydronium, okay, and this base here. But what's also going to happen? This, right? Because if that's weak, what we'll talk about as a relationship is, well, this is strong. So more than likely, the equilibrium may drive further this way. Okay, so that's the biggest difference between a weak acid and a strong acid, and this could also pertain to bases. Okay, a strong acid in water now, it's got to be in water here, okay, it is going to completely ionize. So we'll go over this and over this. Okay, but a weak acid does not, and that's why you see the arrows there. But nonetheless, both of these fall under Arrhenius theory because they have a proton. Okay, here's our proton, and here's a proton. Okay, so they have an H+. That's what a proton is. So let me go back here. Okay. Sure. Because it's how you draw it. Most times chemists will do this, and it does confuse students in the beginning, but it's because when you draw this Lewis structure, which we're going to be doing later, it's this. And so that's the order. Oops, forgot that. That's the order that it's drawn. Yeah, so it's showing you that hydrogen here is the one that's our acidic proton. Okay, so the acid contains hydrogen, okay, or let's say contains hydrogen and produces H+, which we call this a proton or hydronium. Okay, for a base, the Arrhenius theory says the base contains hydroxide, which is OH minus, okay, or a hydroxyl group, what it's called, okay, and it's going to produce this hydroxide in aqueous solution. Okay, so here's two examples. Okay, do you think, well, let's just look at both of these. Are these strong or weak bases? Are they both strong? Yeah. Okay, so should they have a single arrow there? Yes. Okay, if they're strong, that means they completely ionize to form the metal ion here and hydroxide. Okay, so these fall under the Arrhenius theory here. Okay, so I've already said this, but here it is again when you're reviewing. We're going to look at neutralization reactions, and this means that your H+ and your hydroxide combine. So they're going to be very attracted to each other. So if you have this in solution, okay, positive and negative attract, okay, just like a magnet. All right, so if you put the negative ends of a magnet together, what are they going to do? Repel. All right, but if you put one positive and one negative, what are they going to do? They're going to attract. It's the same idea here. Okay, so these are going to be attracted to each other to form water. Okay, so that's what the Arrhenius theory said, is you take an acid, which we would call it just a H+, because that's what we produce, and we can take a base, here's our acid, here's our base, and they can come together and form water, and also a salt. Okay. If we have a strong acid, like I said, here's a list of some, which you have that list and plus some at your seat with you. Okay, and these are aqueous strong acids, meaning that they completely ionize. You'll hear me say that over and over. So they ionize 100%, okay, to form that H+ ion. Okay, and the same for bases. If it has a single reaction arrow, that indicates to you that it's strong, unless I've made a mistake and put the wrong one there. Okay, but you can always check it. And these are strong bases, meaning they completely ionize as well, or dissociate is the same thing. Dissociate means they break apart, okay? And that's the definition for a strong base. Okay, and now just to further talk about our proton here. So protons are generated in acid-base reactions, especially the Arrhenius theory says an acid has to have hydrogen. Okay? But in reality, that proton in water is not just going to be sitting out there by itself. Okay, so when it's in solution, so here's that proton that we produced from the acid. Okay, but in reality, you're going to have all these water molecules. Okay, and this has lone pairs, and they're going to be attracted to it. Okay, so they kind of solvate it. Right, and so we write that as the hydronium ion. Okay, so that's why H plus is equal to H3O plus. Okay, all it's showing is that that hydrogen, that proton, has been solvated by water, and so they write it as H3O plus. Okay, so they're the same thing. Okay, and this is just showing your oxygens where you have a kind of a negative or partial negative charge, and so that's what's attracted to this hydrogen. So that's what makes those attract. Okay. Showing more board space here. All right, now we're going to look at the Bronsted-Lowry theory. So Bronsted and Lowry, imagine that, came up with another theory quite a bit later, so 1923 there. And their theory encompassed more acids and bases, so it was more thorough than the Arrhenius theory was. And it said that an acid is a proton donor. And a base is a proton acceptor. Okay? So if we look here, I've already labeled the acid and the base. Okay, and we'll talk more about this in H3 here. Okay. Water, as you can see, it's one of those, and we'll also talk about it, but it can act as an acid or a base. Depends on what it's reacting with. Okay, so if we have a base, and this is our acid, okay, so if we donate a proton, so think about it here, you have a hydrogen, that's your proton. Okay, if it's donated to this ammonia, okay, it's going to become NH4+. Okay, if it gained a proton, okay, a proton, remember, is not just a hydrogen, it's H+, right? Okay, so that makes the neutral ammonia become positive, right? Because it gained an H+, or a proton. Okay, if water loses a proton, it lost a positive charge, right? And it lost a hydrogen. So it's going to become hydroxide, okay, and have a negative charge. Okay. Here, HBr, hydrobromic acid, is a strong acid. It's on your list. It's going to donate. That's what Bronsted-Lowry says. An acid donates a proton. Okay. So if it donates a proton, so it gives it up here to this H2O, okay, what's this HBr going to become? If it loses its hydrogen. Yeah, and not just neutral, it's going to be negative, right? Because it lost positive charge. Okay. What about our water here? It acts as a base. If it gains a proton, what's it going to become? Right, it gained that proton, and now it has a positive charge. So you wouldn't just write it as H3O, it has to be H3O+. Okay. Okay. Now let's talk about the difference between this theory and our Bronsted-Lowry theory. Did anybody notice anything different so far? Let me go back. Okay. Our Arrhenius theory said that our base has to contain hydroxide. Okay. Does our base contain hydroxide here? No. Okay, so there's one difference. Okay, so we have another base now that's included that the Arrhenius theory did not. Okay, it says acid has to be a proton acceptor, which it is, so we don't really see a difference there. Okay, and we're in aqueous solution. Okay, now look at this reaction. This is an acid-base neutralization reaction as well. Okay, we have HCl, so it's going to be our acid, right? Okay, this NH3 is going to be our base. Okay, so if the acid loses a proton, so it's going to donate a proton to the ammonia, it's going to become the chloride, right, because it lost its proton. Okay, and then the ammonia gained one. Okay. If you look at this, okay, how is it different than the Arrhenius? I mean, I have them all listed here, but okay. One big difference is, where is it at? Number 2. Okay, this reaction falls under the Bronsted-Lowry because we had an acid donate a proton and a base accept it, right? But number 2, it's not in aqueous solution, right? Which is what the Arrhenius theory said. Everything had to be in aqueous solution. Okay, so now we know the true definition doesn't have to be in aqueous solution. We can take an acid and a base, react it in their own solution, and it doesn't have to be aqueous. Okay? Also, it says that we have to produce hydroxide if it's a base, and H plus is if it's an acid. Okay? But here we formed ammonium and chloride. Okay? So we actually made a covalent bond. Okay? We didn't produce just H plus or hydronium. Okay? And then also, so here the amine base, which is our NH3, does not produce hydroxide. Okay? So there's 3 differences, main differences, between our Arrhenius and our Bronsted-Lowry theory. Okay, keep in mind, though, that if you look back here, we still consider this to follow Bronsted-Lowry. So you kind of think of it as an umbrella. So our last theory we're going to talk about encompasses all acids and bases. So we haven't gotten to it yet. Bronsted-Lowry is a little bit lower here. It covers most. And then the Arrhenius covers the least. Okay? Just because this falls under Arrhenius, it also falls under the Bronsted-Lowry too. Okay? So this would be an example of where it fell under the Arrhenius because we have H+, it's an aqueous solution, but it also follows our Bronsted-Lowry theory, okay, where it donates and accepts a proton. Okay, we have a relationship between our reactants and products, and it's called a conjugate acid-base pair. What you're going to do is you're going to look for the one reactant and one product that look almost identical to each other, minus a proton. Okay? So if first step says identify the reactant acid and base. So that's what you have to do first. Okay, so let's do that. I'll draw it on here. Okay, so pick out the acid and the base. Okay? All right, what are we going to label the HNO3 as? Acid. So I was going to call it nitric acid. That would give it away. Okay. Okay, so if it's the acid, then water has to be the base. Okay? All right. Is this an example of an Arrhenius theory acid? Would it fall under the Arrhenius category? Yeah, it's an aqueous solution. Our proton has acid has a proton, okay, and then we form hydronium, or H+. Okay, so remember H+ and hydronium are the same. Okay, does it fall under Bronsted-Lowry? Yes. Okay, it's going to fall under Bronsted-Lowry if it falls under Arrhenius. Okay, and so we can donate and accept a proton. Okay, so our acid is the proton donor, right? Okay, so we're going to donate a proton. It's H+ there. Okay. All right, if you look at let's start with the acid. Okay, which product over here looks just like the acid minus a proton? This or this, right? Okay, so if we draw, that's a little arrow over here. Okay, all that happened was we lost a proton, which that's what our theory says we're going to do, right? Okay, so if we lose a proton, this is called our conjugate base. Okay, and this is an acid conjugate base pair. Okay. The base is supposed to be a proton acceptor, so it gains an H+. Okay. And so this is our base, and this would be our conjugate acid. And that makes perfect sense because H3O plus is an acid, right? That's what our definition, or one of our definitions, says. Okay, so we have our acid and conjugate base, a base and a conjugate acid. You're always going to have this in your acid-base reactions. And how you can tell them apart is just look for one of the compounds that looks just like the acid or base minus a proton. Okay, so we just did all of this in one little swoop there. Okay, we found the ion that looked like our base. So our nitric acid is the acid, our conjugate base is the nitrate, water is the base, and our conjugate acid is the hydronium. Okay, this is the standard format, and you'll see this in your book, but a lot of times when I'm doing these, I just write under it, conjugate acid, conjugate base, base, conjugate acid. This is the standard format for it, so I want to show it real quick. And basically, if you have so HF is our acid here. And so you would label it as the pairs, you give the same number. So there's our acid, and here's our conjugate base. So you would call it acid 1 and base 1. Okay, and then here's your base 2 and acid 2. So this gained a proton, and this lost a proton. Okay, and so the subscript 1 indicates they're the first pair because that's what's written first. It doesn't matter, just whatever's written first. And then the subscript 2 indicates that's your second pair. So you want your pairs to have the same number, basically. So this is just a standard format for writing it. Okay. Notice we have HF. So what did I say about it earlier? Is it a strong or a weak acid? It's a little too weak, yeah. It's right up on the kind of borderline. I think its acidity values, it's still negative, which you would think would be acidic, but it is still slightly weak. Okay, and so what arrows do I have? I have the equilibrium arrows, right? Okay, so that would make sense there. Oops. Okay, so here's the major differences. So you'll have to be able to explain this and recognize this. Okay. The main difference is for a Bronsted-Lowry, the reaction does not have to be in aqueous solution to produce H+. Okay, so Arrhenius said it's always got to be in water, and we found multiple examples of where we do not have to have an acid and base in water. They can react together in whatever solution. Now we use organic solvents and all kinds of things. So, and then bases are not required to have hydroxide in their formula or to produce it. Okay, so over here we said we have to produce hydroxide, but we saw an example just a few minutes ago where we did not. So we had an acid and base react together, and we actually formed a covalent bond. Okay, so we're going to go back to our conjugate acid, conjugate base. Okay. And the idea here is if you have a strong acid then its conjugate base is going to be weak. Okay, so we have an inverse kind of relationship between our pairs. Okay, if you have a weak acid, then its conjugate base is going to be strong. Okay, same idea. If you have a weak base to start with on your reactant side, then your conjugate acid is going to be strong. Okay, if you have a strong base, your conjugate acid is going to be weak. Okay, so that's their relationship. So this really saves us a lot of having to know values. We'll look at some values, not this chapter, but later. But you really can kind of just get them an idea of whether it's weak or strong, just basing it off your table here, and then basing it off your knowledge of a conjugate acid-base pair. Okay, so they have an inverse relationship, so the weaker the acid or base, the stronger the conjugate partner to that. Okay, so now we can label our acid and base and conjugate acid, conjugate base. Okay, and so now our relationship is that we know that they have an inverse relationship. Okay. This is the only weak base that we're going to discuss in Chem 112. Okay. There are derivatives of it. So here's our ammonia, NH3, hopefully everybody knows is ammonia. Okay, if we draw its Lewis structure, looks like so. Okay, this lone pair right here of electrons, that's what's making it weakly basic. And then we can have derivatives of this. So we could have this methyl ammonia. We could have another carbon, CH3. Okay, but all you're really looking for is this nitrogen, and then it has, may have two hydrogens attached, or it could have, so we'll just keep two hydrogens if we need to here. Okay, so I'm not going to do many derivatives. There are hundreds of derivatives that we look at in organic, but for you all, it's either going to be ammonia or a very simple derivative of that. Okay, this is the only weak base that we discuss, because the weaker the base starts to get, then we start to label it as an acid. Okay, so there's really not a whole lot. There's not a whole lot of weak bases, really. Most weak bases are going to have some kind of nitrogen in there. Of course, there's, like I said, there's tons of different compounds that I could draw. Okay, and so if we look at our reaction arrow, we have the equilibrium arrow. So in water, this is a base. So this, you've got to remember this because I'll use it quite a bit. This nitrogen-containing compound is a weak base. Okay, so we're going to accept a proton, okay, and we form a bond here. We form NH4+, and then we form hydroxide. Okay, and we have the equilibrium arrow because it's weak. Okay, here's the other derivative that I drew over here. So it just has a methyl group there. That doesn't really change anything. You still have the nitrogen. Okay, that's what's actually accepting the proton. So on Thursday, we'll look at the actual electrons and how they move. Okay, today we're looking at the protons. Okay, so it accepts a proton. Everything's carried through, except here we have 3 hydrogens now and a plus charge, and then we have hydroxide. Okay, so just to compare this one more time. Okay, when it is stated that something's weak, that means that its conjugate partner is stronger. So that means if it's stronger, more than likely, the equilibrium is going to go this way. So instead of the ammonia picking up a proton, you're going to have the ammonium over here act as an acid and donate a proton. So this is preferred. Okay, so I'll show it backwards here. So the reverse is preferred. This is your base, acid, so instead of this happening, we have, now this is our conjugate acid, which we know is strong. because this is weak. Okay. Then we have our conjugate acid that's strong donate a proton to the hydroxide. So if that conjugate acid that's strong donates a proton, what does it form? NH3 plus water. So instead, the reverse. So a lot of times you'll see equilibrium arrows and one will be larger than the other, like that. And that's just showing that more of this is going to be formed than this. Okay? And if you compare that to something like our sodium hydroxide, which is on your strong base list, you have no equilibrium. Everything is driven to the Na plus OH minus, which must mean this sodium is a weak acid because it doesn't want to do anything with this base. It has no proton to do so. Okay. So it ionizes 100% when it's strong, and then to what extent this ionizes, that's what we'll look at that in a different chapter. So we label, an acid or a base, its strength based on how much does it ionize. And we'll do that in chapter 18. Okay, so we've seen an acid, water act as an acid or a base. Okay, so we're going to talk about that a little bit here. Okay, here's just water reacting with water. Okay, so you probably don't think about this when you're drinking water, but you're actually having a reaction take place. Okay, so the fact that water will react with itself, that's called autoionization. That's just the definition for it, because it reacts with itself. Okay, whereas we've been looking at an acid reacting with the base. There have been different compounds. The fact that the water can donate and accept protons. Okay, so if it can act as an acid and a base, that means it can donate and it can accept. Okay, this is called amphiprotic. I think of ambidextrous when I think of that, somebody that can use both hands. Okay, so if we look here, we can label one as a base, one as an acid. It doesn't matter which one, right? Because they're the same. Okay, so if this acts as a base, it accepts a proton. So we make our acid here. And then our acid lost a proton, and so we get H3O plus and hydroxide. Okay, what's neat about this is that water ionizes and forms hydronium and hydroxide in exactly equal concentrations. Okay, and so that's what we base our pH scale off of, is water, okay, because it is neutral. Okay, and that's because it produces exactly the same amount of acid as it does the base. Okay, so we get equal concentrations of both. And that concentration is 1.0 times 10 to the negative 7. And this will be the basis of our pH scale, which we'll look at the next chapter. So we're going to skip to chapter 18 after this one. And this is going to be our basis behind that. Okay, the fact that water can react with itself, it forms hydroxide, hydronium, in exactly equal concentrations. And we can measure that concentration, and it's always 1.0 times 10 to the negative 7. Okay. It's warm in here again. All right, we're going to look at one of the worksheets for a second, just to kind of take a break from lecturing. I feel like it's been longer than it has. Okay, so you may have this printed out or you may not, so I'm going to pull it up. So some of these up here, we haven't gotten to all this matching, and some of them are, I don't know, you can look them up. They're kind of hard to match up, but we may go over those in a minute. But what I want you to do here is, based on what we've gone over, I want you to identify the acid, the base, the conjugate acid, and the conjugate base. I don't really care. I showed you how to label. You can do base 1, acid 1, base 2, acid 2, or you can just write out, base, acid, conjugate base. It doesn't really matter to me. Okay, but I want you to label these, and then it's going to ask you some questions about the strength. Okay, and that's where you go back to our rule about the inverse relationship with the strength. I'll just give you a few minutes to work these, and then we'll go over them. Get some of your homework done. You can do that. Okay, that would be, yeah, that would be, because see, these match up, right? So this would be A1 and B1, because they go together in those. But you can also just do acid, base, conjugate acid, conjugate base. You can label it that way too. check this one right here. See, it says that in number 2, this is a conjugate acid. So that's a weak base. That's the conjugate acid. So if the base is weak, the conjugate acid would be strong. Number 2. Yes. Oh, you labeled it wrong. Yeah, remember that's the one I just told you, the NH3. The ammonia or the nitrogen containing is always a weak base. Okay, this is your acid, not your base. Yeah, it's got a proton. That's the one I drew on the board earlier. It looked like this. Looks like that. And it's that proton that gets lost. So it gets donated. So that's your base. So that's going to be your conjugate base. Let's see, when it gains it, it becomes H3O. And that's your conjugate acid. Yeah. So this is your acid. That's your base. Do it now. Okay. They look exactly the same, except for the acid lost a proton. See? Here's a hydrogen, or it lost a hydrogen. And now it's lost one, you see? So they're going to look just like each other, except for they're going to be different by a hydrogen. Right. And then for a base, it's a proton acceptor. So it's going to be different, meaning that it's going to have gained a proton. So it's going to look just like this, except this just gained a proton. Yeah, it's the base, so that's going to be the conjugate acid. So you have a acid and base with each pair. All right, we've got nitric acid. I think we already did this one once. All right, so it's our acid. So you can call it acid 1 if you like. Okay, so that makes the water the base. We know it can act as both. Okay. If we look at our acid donating a proton, so it lost a proton, okay, then this nitrate is our conjugate base, or we could call it base 1. Okay, so meaning we want our 1s to match up to be in the same pair. For the water, it's the base, so we'd call it base 2, and you really don't have to do the numbering, it doesn't matter, but there's your base, and then this would be your conjugate acid 2. Okay, and it accepts a proton because that's what the Bronsted-Lowry theory says, and so it's only different in the fact that it gained H+. Okay, number 2. We've got ammonia there. Okay, is it a base or an acid? Base. Okay. I'll call it base 1. So it's going to end up being acid 2. Okay, if it gains a proton, here's its conjugate acid here. And here's our conjugate base. Okay, hydroxide is a base, so if you labeled wrong, and that could be a hint to you. Okay, so the NH3 gained the proton, became ammonium, so NH4+, and then the water acts as the acid in this scenario, and it lost a proton to form hydroxide. All right, this is formic acid, what I drew on the board earlier. So this proton right here is what makes it an acid. And then here's the conjugate base. So it's just different by the loss of that hydrogen. Water is going to act as a base. And the hydronium is an acid, so it'll be, whoops, the conjugate acid there. We're looking at the first one in this next part, says is number 1, so part 2, number 1, is the conjugate base weak or strong? Okay, so we want to know if our conjugate base is weak or strong. Okay, so to figure this out, we go back to our acid. Okay, so our acid is nitric acid. Is it weak or strong? It's strong. Therefore, its conjugate base has to be weak. Okay, if we look at number 2 now, okay, so our ammonia, is it a weak or a strong base? Weak. Okay, I told you it's one of the only ones, so it's weak. All right, then it wants to know, is its conjugate acid going to be weak or strong? Strong, exactly. They're going to have opposite strengths. Okay, and then number 3, is the conjugate base weak or strong? Okay, here's our conjugate base, and there's our acid, so there's our pair. Okay, is formic acid or that formula on your sheet there? Do you see it anywhere? No. Okay, so if it's not on your sheet, then you consider it to be weak. Okay, so that would make its conjugate base strong, right? Mm-hmm. Do what now? Yeah, this was just a printout. It didn't, yeah, so we would have the double arrow there. Yeah, but those are only in water, which all these are in water, where we have the equilibrium arrows. Okay, let's go up and see how we do on this part. So let's try to match these the best we can. A couple of them are a little hard. Okay, first thing says proton donor. What do you think that would match up with on our... We should know this one. A proton donor. Over there. Okay, it's an acid, but in our definition it's the Bronsted-Lowry acid, right? Okay, that's what our definition says. Okay, so we'll put, whoa, what is that? 1 second. Oh, okay. E. Okay, okay, the second one's a little tougher. What do you think NO2 would be? I'll give you a hint. It is between A and F. What do you think you could take NO2 and react it with something and produce? Could you produce an acid or a base? Acid. Yeah. It's called an acidic oxide. It doesn't look very acidic, but when you react it with an acid or even in water, we could react this with H plus and get an acid or even nitric acid. Okay, and so this one is F. A strong electrolyte. Anybody remember what electrolyte means? Okay. Electrolyte is the same idea that when we were in the lab and you had the electrodes and you put them down in solution. Okay, the sodium hydroxide or whatever was supposed to register at like a 9 or 10. It was stronger, meaning it conducted electricity better than the others. So the stronger the acid or base, the better conductor it is, which means it's a better electrolyte, a stronger electrolyte. Okay. Okay. Yep, so this one should be J. Strong acid or base is a good electrolyte. So this is actually the beginning of chapter 18. We talk about that, so we're a little bit ahead here. So E. Okay, yields hydroxide in aqueous solution. We should know this one after today. G, everybody agree? Exactly. Okay, Bronsted doesn't say that. It can produce hydroxide, but it says a base is a proton acceptor. All right, what about 5? Mentioned this quite a bit, and then we didn't go into much detail. We will this week, but take an acid and base and you neutralize it to form salt plus water. Okay, you did this actually a few times. You've done this in the lab, so it's going to be H. Okay, if you have a solution that has excess hydronium ions, what's it going to be? Hydronium, or H plus, is an acid, right? That's what we measure it by. Okay, and a lot of times, see, it's a H plus donor over here. Okay, so if it has excess of that, and it's not neutral anymore, then it's going to be acidic, right? Okay, a proton acceptor, what definition is this? B, Bronsted-Lowry base. What about number 8 here? Okay, so this one's good. We'll be practicing these some. But if you take H2CO3 as your acid, and you draw the conjugate base, you're going to get HCO3 minus. Okay, so all it did, an acid loses a proton, right? Okay, and don't forget, because it's going to get more and more important to remember these charges. Okay, so if you lose a proton and it's neutral, it's going to be negative. So what do we say that was? D? All right, the last two. Lithium oxide. We got two choices here. Lithium, a lot of our bases are made up of metals, right? So we could react lithium oxide and form a base. Okay? So some kind of, whether it's lithium hydroxide or whatever it might be. So we could take that lithium, it's an oxide because it's got oxygen, so we call it a basic oxide because we could react it and form a base. All right, this is a polyprotic acid. Why do you think it's called poly? Protic means what? Probably proton, right? Hydrogen. Okay, so why do you think it's polyprotic? Yeah, we've got 3. So technically, depending on our situation and the solution, it could donate 1 proton, and then how many would it have left? 2. And then it could donate another one and donate another one. So it has 3 protons that could be donated or lost. Okay, so that ends that. I'm planning on doing the whole sheet today, but now you have your first homework sheet done, so everyone should turn that in. Okay, if you came in late today, just a reminder, please try to get in lab even just a few minutes early. Do not be late today. We all need to start together and be on the same page because we're going to work in 2 labs today. So we'd have to sit around and wait for everybody to get done with the first part. So we will have to talk so I can tell you where we're going to break up and how we're going to do the lab. So please be at lab on time and in proper attire, and I will see you at 1 o'clock. Do what? Yeah, they should both be listed on your syllabus. It's chemical equilibrium and Le Chatelet's should be on your syllabus. Yeah. Yep, and the Le Chatelet's is going to be pretty easy for y'all because I'm going to do a demo for it, and you just got to fill in your